In this presentation, we look at synthetic division. In an earlier example of long division, we divided a fourth degree polynomial by x minus 2, and we got this long expression after we did all our work. We can abbreviate this by just writing the coefficients subtracted in each row. If I look at the first row, I subtracted 2x to the fourth plus 4x cubed. Let's just note that we were subtracting a 2, and there was a 4. And then in the next row, we subtracted 1x cubed plus 2x squared. And then in the next row, we subtracted 2x squared plus 4x. And finally, we subtracted 9x plus 18. Let's just keep up with those numbers and assume that we will always have this format, so we always know what the powers of x are. Then we can put this all into a shorter table that looks like this. Instead of a long division table going down the page with 2's and 4's and 1's and 2's and 2's and 4's and 9's and 18's in it, we can have a shorter table. This shorter table is the idea of synthetic division. To divide this fourth degree polynomial by x minus 2, we first write down the coefficients of the larger polynomial across the first line. And then, since we're dividing by x minus 2, which has a 0 when x equals 2, we will put a 2, not minus 2, but a 2 on the far left. So the table begins like this. The first row up there is the coefficients of that fourth degree polynomial, 2x to the fourth minus 3x cubed plus no x squareds plus a 5x minus a 36. Remember that if a coefficient is 0, to include it. And then on the left, in the next row, we have that 2 because we're dividing by x minus 2. When you divide by x minus c, write c down. This 2 on the far left is a potential 0 of our polynomial. It's the c in f of c. Now, we use this 2 throughout the problem. First off, we're going to add the two rows. At the moment, one row is empty, so treat a blank spot as a 0. So I pull down a 2. Then I take that 2 and multiply it by the 2 on the left to get 4. Add minus 3 and 4 to get 1. Take that 1 and multiply on the far left by that 2 to get a 2. Add the 0 and the 2. Multiply, add, multiply, add. Now this expression gives us our answer. It says basically that this fourth degree polynomial, when divided by x minus 2, gives a quotient that involves 2, 1, 2, and 9. That's 2x cubed plus 1x squared plus 2x plus 9. And the very last term, that minus 18, is the remainder. Or we could rewrite it this way and say that the fourth degree polynomial we started with is equal to x minus 2 times that quotient. The quotient comes from the 2, 1, 2, 9 on the last row, and then a remainder, minus 18, is the last term on the last row. Let's do some more examples. Suppose we want to divide this fifth degree polynomial by x minus 2. Again, c is equal to 2 here, since it's the root of the divisor x minus 2. We're going to write out the coefficients of that fifth degree polynomial. Notice that the coefficients are 3, 0, minus 7, 0, and 10. No, they are 3, 0, minus 8, 0, minus 2, 10. We have that 2 near the corner of our diagram that comes from the x minus 2. The first thing we do is we pull down the 3. Then we multiply 2 and 3 to give us a 6. Add that column, 0 and 6, to get 6. Multiply 2 and 6 to get 12. Add that column to get 4. Multiply 2 by 4 to get 8. Add the column. Multiply by the 2. Add the column. Multiply by the 2. Add the column. The bottom row, there are 6 numbers in it. The first 5 represent the quotient, and the last one, the 38, is the remainder. So when we divide this fifth degree polynomial by x minus 2, the quotient is 3x to the fourth plus 6x cubed plus 4x squared plus 8x plus 14, and our remainder is 38. which we could also write it this way. This fifth degree polynomial is equal to this fourth degree quotient that involved 3, 6, 4, 8, and 14, divisor x minus 2 plus remainder 38. One more. Let's divide the same expression, this time by x plus 2. Since we're dividing by x plus 2, c is minus 2, because minus 2 is a 0 of x plus 2. Write down the coefficients again. I think I've made the same little error. The coefficients are really 3, 0, minus 8, 0, minus 2, and 10. And so I begin my synthetic division this way. I pull the 3 down. I multiply the 3 by the c to get minus 6. Add the column. Multiply by the c to get positive 12. Add the column. Multiply by c is minus 2 to get minus 8. Add the column. Multiply by minus 2 to get 16, add the column. Multiply by minus 2 to get minus 28, add the column. There's our answer. These 6 numbers, the first 5 numbers are coefficients of the quotient, and that last number, minus 18, is the remainder. So here's my answer. When you divide this fifth degree polynomial by x plus 2, you get that quotient, 3x to the 4th plus 6x cubed plus 4x squared minus 8x plus 14 plus what's supposed to be a minus 18 over x plus 2. Is that bottom one correct? There we go. This is correct. While we're at it, let's go back and tell us what the remainder theorem says about this. Suppose you have this function that's a fifth degree polynomial beginning 3x to the fifth, and suppose you want to plug in x as 2. Instead of plugging in x as 2, we could just use the remainder theorem in our work on the previous slides. Notice on a previous slide that when we divided f of x by x minus 2, we got a remainder of 38. So f of 2 is 38. If instead you want to plug in a minus 2, then divide your polynomial by x plus 2 using synthetic division, and the remainder of minus 18 is the value. Remember that when you divide by x minus c, the remainder is f of c. In the next presentation, we will examine complex numbers.